Hello, everyone. My name is Yuhao. I'm a PhD student from UC San Diego. Today, I'm going to present our work on distributed deep learning on data systems. This is a joint work with my advisor, Arun, and our collaborators from VMware. Here's the outline. I will first give a brief introduction, followed by some details about the approaches we evaluated, finally, the experiment results. First topic is in DBMS, machine learning. The goal here is simple. We want to run machine learning algorithms on DB resident data. Generally speaking, there were three waves of work in the past 2 decades, beginning with these data mining tools that implemented a few machine learning algorithms. Then there were efforts like Apache MATLAB and Spark MLab that provide unified abstractions and more complex machine learning models. The third wave, we saw the cloud vendors provide support on their platforms as well. Now, in the past decade, there has been this revolution of deep learning, and it's been so popular and widely adopted. In this context, now they increasingly ask the question is how we can enable seamless support for deep learning over DB resident data. That's what this work focuses. We evaluate the how here and hope our work can help cloud vendors and our fellow researchers. First question, why do we care about this topic? Why don't we just export the data to a data lake and run machine learning there? First, because in DBMS, machine learning provides a familiar SQL interface to the DB users and business analysts. Second is the ease of governance. This has always been important, but recently got a renewed urgency due to regulations such as GDPR and CCPA. And DBMSs already provide good support for governance and provenance. Last but not least is the mature distributed execution engine that a DBMS provides. We heard that sort-out deep learning tools are often criticized for being difficult to set up, operate, and debug. DBMSs have a potential here to bridge the gap. We don't want to re-implement deep learning using SQL or build our own DBMS for deep learning because these deep learning frameworks are already popular among the users, and we want to make the adoption easier. Second, these industrial grade deep learning tools provide advanced compilers and algorithms that we can leverage. So instead, we want to integrate an existing deep learning framework into a training scheme into existing data systems. And there are multiple choices for the training schemes. Each has different parallel scheme and communication pattern. Some are more suitable than the rest. Question is, which framework is a better fit and how do we integrate them without modifying the DBMS? Answer the first question. Our choice is this new system called Cerebral and the novel training scheme called Model Hopper Parallelism, or simply MOP. Not only because Cerebral is our own research project, but also because it's efficient. It works on sharded data setting, just like MPP databases. It offers fast model convergence. In the end, it's also model selection first. Model selection is the process when you tune the hyperparameters and select the model architecture. It involves training multiple models at the same time. This is vital for better model accuracy. There are some alternatives. Task parallel frameworks don't work on sharded data. Model averaging has bad convergence. Parameter server and ring or reduce are bound by their heavy communication cost. We have some more details and analysis in the paper. Okay, with that fixed, now a brief introduction to MOP. It takes a model selection workload, which contains multiple models to train on some sharded dataset, potentially distributed to multiple nodes. It first assigns each model to one shard and let the nodes train the models with their respective data. This is called one sub-epoch. After which, we hop the models to different data shards and repeat another sub-epoch until each model has visited each data shard. This is called one epoch of training. We now try to integrate this parallel scheme into a DBMS. And there are multiple possible approaches to do that. We consider 4 canonical approaches to evaluate. I will cover them in more detail. Note these approaches are not limited to MOP. We can also use them to implement other deep learning training schemes as well. Okay, the first approach is through the UDAF extension of the DBMS. We basically translate the deep learning training tasks into UDAFs, which then invoke TensorFlow for deep learning. The pros are ease of governance, and it fits in existing design patterns such as MATLABs. In fact, this approach has been adopted by MATLAB. The cons are overheads accessing data with the DBMS to Python and TensorFlow, and there are synchronization barriers imposed by the DBMS. I won't go into the detail here, but MOP is largely an asynchronous method. So we had to force MOP to work in the sync mode with the UDAF. This may hinder efficiency when the workload is imbalanced. Next approach is what we call concurrent targeted queries. It's mainly designed to bypass the sync barriers. We dissect the training query into multiple queries with some tricks so that the query planner of the database can send targeted plan to each node, and they can return asynchronously. Cons are still the data accessing overhead, and this may potentially violate some design code. I have mentioned it took time to access data from the DBMS. So to bypass that, we devised this direct access approach where we query the catalog from the DBMS and figure out the location of the physical files, and we just directly access them and cache them. With this, we can use whatever standalone deep learning framework as is. We call this in DB, but not in DBMS, because the database is still, the DBMS still governs the data, but it doesn't, it's not involved in the training process. Pros, efficiency, but it's specific to the DBMS's physical file format and not so portable. We know that there's this new envisioned data warehouse architecture called Lakehouse that proposes to use open file format like Parquet for DBMS, which could potentially help a lot here. Last but not least is the export data approach. It has good runtime performance, but there's a loss in the ease of governance. Okay, now it's time to see some numbers. Here's the experiment setup. We used an 8-node cluster. In addition to MOP, we also include comparisons with other training schemes, model averaging implemented as a UDAF, and ring or reduce. We used PyTorch and implemented it as a DA approach. First, on the runtime and resource utilizations, we see that DA Cerebral, along with Cerebral Spark, they dominate, followed by model averaging, UDAF MOP, and CTQ MOP. The ring or reduce methods, PyTorch DDP standalone with data export, and PyTorch DDP with DA. Like I mentioned earlier, these are heavily bottlenecked by the network cost. And they also use GPU for communication, hence they have very high utilization here. And as you can see, they used almost 2,000 times more network than the rest methods. In terms of model convergence and validation error, only model averaging has worse, the rest are equivalent. To summarize here, model averaging has convergence issue, ring or reduce is bottlenecked, MOP is generally more efficient and converges fast. And in terms of the 4 approaches of MOP integration, we have a trade-off here. The less ease of governance, the better efficiency we got. You can find many more details and experiments in the paper. Okay, last slide. In conclusion, we found that MOP is a good option for in-DBMS deep learning. It's possible to integrate it without modifying the DBMS, and there are 4 plausible approaches we evaluated. In the paper, we evaluated them on 6 axes of comparison in total. Here I only show the 2 most important axes, the ease of governance and efficiency. There are many more trade-offs between these axes. Here are some resources if you are interested and want to learn more about this work. Thank you.